All right. After the introduction to the structure of MOSFET, we can go further to check the detail for their operation. From the very beginning, I would like to tell you what's the operation principle in linear mode or the so-called trial region. Where is trial region? What you learn from microelectronics actually is here, saturation. Okay, but there is the but the overall trial region. Anyway, where is the linear mode? Because if you look at here, the very beginning of the trial region, you can see all those lines will look like this, linear lines. Why? But anyway, it is linear here, but gradually the slope becomes smaller and smaller, and finally, in theory, becomes zero. It means what? In saturation region, never mind how large you apply the voltage to drain, the saturation current is still the same. I mean, in theory. But why? Okay, yeah. Again, from the very beginning, after you apply enough voltage, what does it mean? VGS, not, oh, okay. Why we have S here for NMOS or even for PMOS? Source usually is the common node, reference node, okay? For example, we ground this source. That is the usual case, but not always, all right? So source voltage is for reference. And from very beginning, if there's no voltage here, then from the beginning, VDS equals 0, okay? And then we apply gate voltage, I mean according to source, because source is the reference node. So VGS, after we apply more than threshold voltage for VGS, bingo, as I said, we can generate an effective channel, an inversion layer. Okay, but the more voltage above VT, it means what? The more carriers you can attract to here, right? So the thickness, keep this in mind, the thickness of the effective channel actually is proportional to what? To this. The more above VT, the more carrier proportionally. The more carrier can be attracted here. So the thickness of the channel will be more. That's it. Yeah. Anyway, this is only a cross-sectional view, but this is a three-dimensional device. So allow me to take it out. I'm too lazy. Yeah, I have no time. Sorry, I have no time to have a better one. Actually, a better one should look like this. Okay, but I just Google online to get this for you. Yeah, so just pretend. This is the thickness, the height. The thickness actually is proportional to this. Okay, and then this is the effective length, not the length you draw. No, yeah, the length you draw minus 2 LD, blah, blah, blah. I mentioned already. So this is the effective length, and that is the width. That's it. So for the channel, it looks like this. That is the rectangular parallel pipette, 长方体. Okay, or we call it cuboid. The same. Anyway, yeah. It looks like what? A resistor, right? So what is the resistance? The resistance should be, again, proportional to the length, right? And inversely proportional to the cross-sectional area. So what is the cross-sectional area? The depth, the height, and the width. But I told you already, the thickness, the height, actually is proportional to this. Okay? Oh, and then we know for a resistor, I equals V by R, but R proportional to this. So V by R. Finally, we have that. We have this. Okay? The current actually is proportional to the width by L. Reasonable, right? And also proportional to the thickness. Quite reasonable. Got it? That is from the very beginning. If you have such kind of, again, rectangular parallel pipette, yeah, according to Ohm's law, you will get such kind of current. So it means what? The more VGS, VGS over VT by 1 volt, by 2 volt, by 3 volt, by 4 volt, the slope will be 1, 2, 3, and 4 proportionally. But that is from the very beginning because you have such kind of parallel pipette. Okay? And then you need to increase the voltage here. Because from the very beginning, if VDS is very small, this is for very small region. I mean, the VDS is very small. So you don't have too much impact on the shape of the channel. Okay? But if you further increase the VDS up to the right, you further increase it, what will happen? Don't forget that the thickness of the channel is proportional to what? The voltage difference between the gate and the channel. Never mind at which point, okay, minus this one. But after, so you can see, I help you to plot this. For example, this is the source reference, and that is the gate we apply, right? And this is the threshold voltage. Okay, so from the very beginning, the source is here, the drain is there. So we have such kind of, from the view of gate, I'm larger than you, more than VT in this, larger than VT with such amount from source to drain, because from the beginning, the drain voltage is very close to source. Okay, but after you increase the drain voltage, how will you been? You. Okay, that's too much. Later, I will explain that. But right now, let's focus on this. Again, source and drain from the beginning, and that is VTS. Okay? Or VTH even further. Anyway, if you, for example, if you increase the source and drain to here, the more drain voltage, to the right, the more VDS. What does it mean? Here, see, my voltage, to the left, my voltage is more than VT with this amount. Okay? And how about here? Because it is reduced. Right? It is reduced. The voltage between you and me actually is less than this. So the effective voltage will be reduced by this amount. So the thickness will also be reduced, right? Right? So what you will get is not this one. No. Forget about it. You will have, okay, allow me to show you. Because this is source, that is drain, the drain voltage becomes higher. So between gate and drain, not so much above VT. So the thickness will be reduced. All right? So it will become what? The depth will become this to that. Okay? So you will have a, we call it this one. trapezoidal parallelepiped. Okay? Yeah. Anyway, if you go back here, to the left, the thickness is the same. To the right, the thickness is reduced. So, tell me, how about the resistance? Increased or decreased? Decreased, right? No. Again, the resistance is proportional to this, right? So here, no change, but there, this is reduced. So on average, in the middle, that is the easiest way. Because it is homogeneous increase from here. No. The thickness is homogeneous decrease from here to there, right? The same width, the same length, but the thickness is reduced from left to right. Okay? So it means what? Since the more voltage you apply, the less average cross-sectional area you will get. So it means what? Okay? But according to current to voltage, I equals V by R. Because R is increased, so what does it mean? The slope for I will be reduced. Okay, anyway. Do you know? According to small signal operation, the slope of IV curve equals to what? Right? The slope of IV curve equals the reverse of your resistance. But right now, the more voltage, the more resistance. It means what? The slope will be reduced. Okay, so from the beginning, it is linear. But gradually, after you increase the VDS, the slope will become smaller and smaller and smaller, right? So it means the curve, this is a perfect ideal resistor for its IV curve. It is a straight line. But according to the deformation of the channel 会变形. So more and more, with larger VDS, more resistance you will get. So it will go this way instead of that way. Okay? If it goes that way, it means what? Oh, the higher voltage, the smaller resistance. It doesn't make any sense. For my microelectronics, how I grade my students, I wouldn't like to have some kind of equation derivation for them. No. I have some kind of selection. Okay. Well, for such kind of curve, please choose one. How about IV curve? Oh, this one, oh, that one, oh, this one. After they choose even the correct one, right? They need to explain. That is in which way I can grade, I can evaluate the learning performance of my students. No derivation. For concept proving how good they learned from my class. It is totally different from the other universities, even from NTU. I still think I'm much better in teaching. Why? Because my student in quality is worse than them. So we need to put more effort. I'm not talking about you, no. Anyway, the professors on our campus, on average, how can I say, spend much more time than in NTU. With the most talented students in Taiwan, actually you don't need to teach anything. The student can study by themselves. If they have any question, especially in my era, if I have any question, don't ask the professor. Why? They are worse than us. So you get nothing from the professor. Usually, the help is from our classmates. But that is only in the past. Right now, it is reversed because the most outstanding students go for medical doctor programs, right? So right now, the professor is here and the student, even in NTU, professor here, student there. So I guess my juniors, they can get some help from the professors instead of nothing, okay? Yeah, anyway, I explained this for you. Hopefully, you get all the idea. But you may be curious because the slope from the beginning is the largest and gradually is reduced according to the deformation, right? The depth at this side become here and there and there. So when it will become 0, in idea, when the shape here, the cross-sectional view here, from a rectangle all the way to be a triangle. To be a triangle means what? There is the dead end. I mean, at drain, the thickness is what? 0. So what is the voltage here? Again, the thickness is proportional to this, right? So it means what? VGD. Here, if you would like to make the thickness exactly 0 at D, exactly, okay, at D, then VGD. Okay, yeah, sorry. Needs to be VT. Exactly. The gate to the drain, 1 VT. In idea means no voltage for you to attract any kind of carrier here to make any kind of depth for the channel. That's it. It will become a triangular shape. So we call it, that is a triangular parallel pipette. 三角体. Okay, that's it. That is for the so-called, we call it pinch off. Later, yeah, you'll get the terminology. Okay? At the pinch off, there is no way for you to increase the current, right? Because it is already chopped. No more current, that's it. Even you increase the VDS, no help at all. I mean, in theory, so the current won't increase anymore after pinch off. The slope will become 0 in idea. Okay? So that is the definition for saturation, because you have no any kind of possibility to increase the current. The current is saturated. That is the definition for saturation region. But if you are asking me how much the current will be, okay, without any derivation, okay, from the very beginning, the slope I show you already is proportional to this, right? And when it will be pinched off, again, another VGS minus VT. So what do I mean? If from the very beginning, I can run 2 times faster than you. From the beginning, my speed is 2 times faster than you, right? And then I can run 2 times longer than you. So finally, how much is the total distance I can run? 2 to second power, right? So from the very beginning, my slope is such larger than you, yeah. And then how long I will get pinch off? The same. The more thickness here, right? The longer I can run until it pinch off, right? So another VGS minus VT there. So totally, the current is proportional to the square of this, okay? To VGS minus VT square. So you can see the squared means what? This by that. The first is from the beginning, my thickness more than you, right? And so I can conduct more current. This more current than you. And how about the second term? I can operate such more time than you until pinch off. Okay? So after saturation, my current definitely should be the square of this one. Okay, proportional to this. And also, I have the other one for you, the W, the L, right? So right now, I have to explain the saturation current here should be proportional to W over L VGS minus VT squared. Proportional to means what? You have some kind of constant. Okay. So if you are interested, you can go to get 1 minus 2 mobility COF. Here mu n, right? That's it. That is a proportional constant for all of them. Okay. So how much? I don't care. I help you to get this one because they are proportional constant. Who cares? Okay. Without any derivation, I help you to explain the saturation current look like this. Okay. I help you to explain this, and that is your own duty. Why? The proportional constants look like that. Derive it by yourself. But at least I help you to explain the saturation current look like this. It is proportional to W, reversely proportional to L. Right? We call it aspect ratio, 中横比 W over L. Aspect ratio, very important parameter for analog IC designer. And then the squared, especially I help you to explain why it is squared. It is not only the first power, or why it is not the third power of this. No, right? Okay, that's it. Hopefully, yeah, you get deeper understanding in my class. Yeah, compared to microelectronics in the past, or even you go to NTU. I don't think the professor will explain this for you. Okay, they simply don't need it because the students are so talented by reading. Oh, they get all the points. They get full understanding. Oh, luckily enough. Okay, now aspect ratio here. Okay, that's it. Very important idea. Yeah. Actually, I derived this for you. Where? Here. Okay? The same concept. Exactly the same concept. Yeah. So again, from the very beginning, you have more than this, right? So you have such kind of rectangular cross-sectional view. Okay, and after you pinch off, right? Here. Yeah, that's it. You may be curious. After pinch off, in theory, we told you the current won't be increased. Okay, but is it real? No, in practice, no. Why? Because after pinch off here, if you increase the voltage even further, what does it mean? The pinch off point will be shifted from drain a little bit to source, right? So what does it mean? It will look like this. See? Get it? So what is the difference from here to there? I mean, again, all those, for all equations, the main component is channel. We focus almost on channel instead of the others. The others only support the operation of channel. Okay? Now this is a very important idea for you. But anyway, what's the difference? Pinch off here or in the middle of the channel? What is the difference? According to the resistance, you can see it is again, right? How about A? The same. Why? According to the main body of the channel. From the left, yeah, the thickness depends on VGS minus VGH. Here and there are the same. And how about the right? The same, 0. So, on average, the thickness is this by 2. Okay? Maybe 1/2 for saturation, yeah. Okay? The average thickness. So what is the major difference from here to there? The length. The length is reduced a little bit. Okay? Got it? We call it channel length modulation. If you how can I say? If you increase the drain voltage, then the channel length will be reduced. If you decrease it, then it will be, the length will be increased, right? So higher, shorter, lower, longer. You can see, yeah, you can modulate the channel length. That's it. Allow me to point out that, why we only focus on this? Because here are N, they are P and N, right? So from N to P, to the depression region, and then back to N, it depends very much on diffusion. And inside the channel by drift, okay? Diffusion, I told you already, depends on the concentration difference, or the differential of the concentration. Oh, you can see a lot of electrons here, almost zero there. A lot of electrons here. So you have, how can I say, almost infinite tendency to penetrate from the channel to the depression to the subject, and also go back to N+. It means what? The resistance caused by diffusion is almost zero. I mean, nobody would like to stop you. Yeah, because, we have a lot of electrons here. They will be more than happy to go there, right? Then penetrate back. Okay? So the major resistance to stop the current flows from, how can I say current? The electrons flows from source to drain. Actually, is the channel itself. Nobody, almost nobody would like to stop such kind of electron flow. Okay? So the main resistance is provided by the channel itself. Anyway, anyhow, yeah, this is the blah blah blah. And I need to show you this. After pinch off, if you increase it, then the length will be reduced, right? So you need to change this from L to L prime. L prime means what? Effective length. Okay, that's it. Then we can go further. What parameters decide the magnitude of the current after saturation? Wow, a lot of them, right? The length, the width, the threshold voltage. Okay, a lot of them. I explained already. So, yeah. For such kind of long channel, later I will show you some kind of short channel effect. For regular channel MOSFET, you can see, again, I told you, the saturation current is to the square of this one. Okay, so we have some kind of quadratic distribution, the second order. Okay, quadratic. Here, dependence. Hey, what's the matter? Oh, yeah. Anyway. The saturation current is proportional to the squared of VGS minus VTH. Okay, so we call it quadratic. All right? Yeah. Another very good example to clear your mind about analog IC design. Yeah, I mean, compared to digital ones, you need to get even further. You need to, how can I say, to understand the property, the operation principle in much more depth than digital IC designers. Allow me to point out this, transconductance. Okay, trans means transform. Yeah, conductance means what? I for V, right? But trans means the input and the output don't happen at the same port. Okay, so from the input port, usually gate, and output usually drain. Okay, usually, not always. So I would like to say, from the output current at drain and the input voltage at the gate. Okay, how much you can get? That is, yeah, you excite the device from the gate, okay, by voltage. Then how much you can get at the output? I mean at the drain for the current. That is the definition for Chen's conductance. Okay, but piece of cake, right? Yeah, you can see. Oh, that is the output current, and this is the input voltage. So if you would like to get such kind of Chen's conductance, you just have such kind of partial differentiation, right? Differentiate. Yeah, because why partial, not full? Because it is influenced by not only this, but also the width, the length, many kind of parameters. Okay. Yeah, anyway, so GM means this. Okay, so you get that from the very beginning. Okay, you can do it by yourself. Very easy. Okay. So what does it mean? It means what? GM versus your, for example, your VGS minus VTH, or your W over L. Okay? Yeah, you can see, if you look at GM versus effective voltage, effective more than VTH means effective or overdrive. Overdrive, okay? Anyway, they are linearly dependent on each other, so you get this one, GM and this. Look nice. But if you go further, you say, hey, look, for this one, that one, right? If you move to the left, then have the square root, you will get this one, right? So, whoa, you get this. It means what? The GM and the bias current, it looks like that, the square root. Okay, but we can go even further. Yeah. If you leave, because this is square, right? Squared means 2 by 2, 1 by 1, right? So you move all this to the left, we get only one. We get only the first order, right? So we get this. That's it. Okay? Yeah, they are all correct. But in this way, wow, what does it mean? How about the relationship between GM and overdrive voltage? Oh, wow, see? They are reversely proportional to each other, so it looks like this. But from the beginning, from this one, it looks like that. But from the final one, it looks like that. Which one is correct? Which one is correct? In theory, all of them. Okay, all of them are correct. But why? Here, we have linear dependence, right? And there, we have reverse dependence. Why? They are all correct, I promise you. Okay? But in practice, which one is correct? I can say, which one is closer to your circuit operation? Yes. Yeah, just forget about the middle one, okay? Because GM over versus effective voltage, GM versus effective voltage, they are totally contradictory to each other, right? So, anybody? Which one is more practical? I mean, for your IC design, for your circuit design, which condition? Because both are correct in theory, but in practice, which case you will face more frequently during your IC design? The left or the right? Anybody? Anybody? Actually, the right. Why? I guess from the very beginning, I told you for CMOS circuit design, usually we focus very much on bias current instead of bias voltage. It means what? From the very beginning, you will set the bias current to make it fixed. If ID is constant, sorry, it looks like this. Okay? Usually, you can say, hey, W over is constant. No. What I told you, for the designers, they usually fine-tune the aspect ratio in front of your computer. Right? Right? So usually, this is not fixed. Usually, bias current is fixed. So you fine-tune your W over L, blah, blah, and you will get this. Okay? Yeah. So that is really upset. Don't expect under fixed bias current, you get more overdrive voltage. You will get better transconductance. No. Yeah, reversely. The more overdrive voltage under fixed bias current, you will get less. That is a really upset result for you. But that is the ugly truth. And then we can go for second order effects, for example, body effect. What does it mean for body effect? Okay, anyway. That's too complicated. From Professor Razavi's textbook, I would like to tell you that, even in the channel, right? Inside the channel, for MOS, inside channel, it is N-type. Out of the channel, the subject, the body is P-type. So you have depression region, right? You have depression region, okay? And in chapter 2, I told you already, the more reverse biased, the wider depression region. Got it? Got it? Okay, so you can guess, if the body voltage is reduced, becomes more negative because body is for P-type, channel is N-type, right? So what does it mean? The more negative body voltage means the more reverse biased. So according to chapter 2, the more bias for such kind of P-N junction, the wider depression region. So it means what? For the thickness of the channel, it will be reduced. Got it? From the beginning, you will say, hey, at the channel, the cross-sectional view look like this. Sorry for that, because this is N, that is P, so you have depression region. Okay? So if you lower the bias voltage, it means what? The depression region will be expanded. Okay? Both to N-type and P-type. So the thickness of the channel will be reduced. It means what? More resistance. Right? More resistance means what? The less current. That's it. Bingo. Okay? So, what is body effect? Through my explanation, right? VB for MOS, if VB is reduced, the saturation current will also be reduced. On the contrary, if you increase VB, right, also you can increase the conduction current, because if you increase it, then the depression ratio will be reduced. The effective thickness will become more to conduct more current. The lower VB, the lower current, the higher VB, the higher current. The behavior is much similar to your gate, right? The higher gate, the more current, the lower gate voltage, the smaller current. Bingo. What do I mean? Body in the behavior actually is quite similar to gate. Okay? So you can think body is the second gate to control the current flow between source and drain. Okay? But it is not so effectively because body can only indirectly influence the thickness. For gate, it is directly. For body? No, because it controls what? It controls only the depression region. And especially this is M+, I mean for channel. Okay? So you have much less impact on channel depth than the gate. The efficiency is not so good. Okay? So that is for body effect. Okay? Again, body can be viewed as second terminal for the gate. Okay, but the efficiency for current control is much less than the original gate. That's it. Yeah. And since body can also have some kind of influence, some kind of impact on your current, right? If the direction gate can influence the original one, right? They are influenced by the gate. Okay, and how about the influence from the body? If the impact are the same, I mean by the gate and by the body, if they are the same configurations, you will get more current. Okay? On the contrary, if they are reversed to each other, then the current will be reduced. So, what's the real situation? Again, it is both are, I mean both are possible. If I increase, you also increase, then configurations, okay, you will get more current. Right? On the contrary, if I increase, you reduce. Oh, sorry for that. They will be contradict with each other, then the total current will be reduced. So again, the answer is already on the screen. Okay? On the screen, you can see with body effect, usually they are contradict each other. But why? Later I will show you another very good and practical example. Okay? So according to Murphy's law, what you dislike is more likely to happen. 你越讨厌的越容易发生. So don't expect gate and body will synchronize with each other. No, they are usually they are reversed in operation to each other. Okay, that is really upset. Yeah, it is possible to make them synchronize to each other, but you need to apply very special design. Okay, it is not impossible, but harder to achieve. And again, the other concern is, never mind how much body voltage you would like to apply. Don't make the body and the channel forward bias. Okay, otherwise you can see, we only focus on the current from drain to source, right? If body and the channel is conductive, is forward bias, then a lot of current will flow to the substrate. I promise you, it will only waste your power. Okay, no much benefit you will get. So never mind how much voltage you apply to the body, even though you can make the body and the gate synchronize with each other, right? Yeah, congratulations. You can help them to conduct more current, again, from drain to source, not from drain to body. Don't make the body contact, the body to channel conductive, I mean forward bias. It is really dangerous. Till now, to my memory, nobody did such kind of design with forward bias from the body to the channel. No. Okay? We have somebody, yeah, apply the voltage to your body to get some more benefit, usually to increase the overall GM. Overall GM means what? GM plus GMB. Yeah, GM is for gate by definition. So we have another B, okay? And it means the impact from the body contact. But anyway, usually they are reversed. I'm positive you are like, that is really bad. Okay, but for some specific circuit design, you can synchronize both. I'm positive, you are positive. I'm negative, you are negative. Congratulations. You can increase the magnitude of the overall GM, yeah, to get better again. Okay, I0 over VI, blah, blah, blah. Okay, yeah, it is possible, even though it's much more difficult to control the current by the gate, but it's still possible. Okay, moments ago I told you I would like to have one very good and practical example for you. See, this is the so-called source follower. Yeah, to amplify the current instead of the gain, right? From the very small signal, usually we apply common source. Yeah. Okay. For common source, the gain will be quite large. But how about the current gain? Very little, around 1. Okay. So you amplify the signal from very small to large enough. Then, if you would like to drive a heavy load or of chip to drive something out of the chip, you need to have good enough current. All right, because from common source, you have good voltage gain, but very bad current, almost no gain for the current. The current is really small. So to drive the output load, or a heavy load, you need to, on the contrary, amplify the current instead of the gain. That is the function for such kind of source follower. Instead, AV is almost 0. Okay, almost 1. But we can, amplify the current very, very much. Okay, so what you learn from microelectronics, you have many kind of equations for such kind of source follower. You learned already, I promise you. Okay, and also for such kind of AV almost 1, AI much larger than 1. That is the conclusion from your microelectronics. Okay, and then you can see, the V in is variant. For example, sine wave, right? Or your audio signal, something like this for our voice. Okay, to amplify the voice, to drive the speaker, you need very large current. So we need the help of such kind of source follower. Okay, since AV is almost 1, so what does it mean? After derivation, we have such kind of blah blah blah. Okay, the current look like this. Okay, anyway, you can see in brief, we have, usually we will say VR equals V in minus VTH minus delta VD as a saturation, blah, blah, blah. Okay? If they are fixed, because the current is fixed, then delta VD as I suppose is to be fixed. Then if VTH is fixed, congratulations, the difference between VI and from V out and your V in should be fixed. Okay, so I'm here, the V in, and then the V out. I becomes higher, you becomes higher, I becomes lower, you becomes lower. Okay, so the difference is fixed from microelectronics. The more V in, the more V out, and the difference is again VTH plus VD, etc. Okay, something like that. Oh, okay, I forgot to remind you that we put almost all the blame on VTH. 我们把所有的过错都堆到 VTH 的身上。that is easier for teaching the students, especially it is easier to teach the new engineers. So according to body effect, we put the blame on VTH, almost everything. Later, I will have much more examples for you. Okay, Yeah, anyway, for all those current variation, not only the gate voltage can have some kind of impact on this, and all the others, again. So if in practice, the body and the gate, they are different, okay? Yeah, they have different reverse impact on the current. It means what? The more body effect, it means the less current you will conduct. I mean, in practice, usually that is the case, okay? And you would like to put all the effect on VTH. Since I told you, usually the more body effect, the less current you will get. So equivalently, it means what? The more body effect, the higher VTH. Got it? Higher VTH means the total current will be reduced. Okay? So we put the blame on VTH instead of the body. That's it. Okay? For you to get some kind of easy understanding. Then we focus on here. From microelectronics, no body effect. I cannot say microelectronics is incorrect. No, because that is a very fundamental study for the students, so they don't focus on this no body effect. Okay, that is the case. No body effect, so VTH gets no impact from body effect. VTH is the same. So I told you, yeah, V out means V in minus VTH minus delta VT. All those are fixed. So you have this one. Fixed difference. From here all the way to there, the difference, the delta between V in and V out should be exactly the same. Okay? But how about with body effect? How about that? It will look like this. Okay? Yeah. Why? Because the higher V in means the more V out, right? The more V out, this is for source, and the body is still connected to the ground. So VBS will become even more negative. And I told you, even more negative, more reverse bias, right? Less channel depth. So less current for you. We put the blame on VTH. So it means what? Higher VTH. Higher VTH, it means what? From here, VTH is smaller. From there, VTH is larger. Right? So the curve looks like this instead of that. Here, larger, there, less. No, forget about it. Okay? Oh, it's really upset. Why? Because if you have a sine wave to be amplified, then to drive the speaker, you will get a lot of distortion according to this. Without body effect, congratulations. Yeah. The sine wave from the input, will be reduced for a fixed amount without a body effect. All those delta, the difference is fixed. So the input is perfect sine wave. How about output? Output is also perfect sine wave. Only shifted down a little bit by delta V. Okay? But according to body effect, the impact is totally different. Yeah, again, this is the good sine wave. But for higher voltage, it means what? The delta will become larger. And for the lowest one, it will become smaller. So you will have something like this. Okay? More difference here, less difference there. Okay? So is it a sine wave? No, it is not a sine wave at all. It is distorted. Okay? So according to such kind of distorted sine wave, but the fundamental frequency is still the same. According to Taylor series expansion, 泰勒展开式。 from the beginning, I mean, in the spectrum, you have only one line for the sine wave, right? That is for the input. And how about output? Because the sine wave is distorted and output, according to Taylor series expansion, you have not only this, but also the second, the third. Wow, you have a lot of harmonics. It is really bad for the sound quality. Okay, that's it. That is the ugly truth. Okay, if you apply everything from microelectronics to real electronics, I promise you, the quality will be really, really bad for you. Okay? What you can do? How can you make this? The key point is no body effect. Can you make it? How to make it no body effect? It means the VBS should be constant. So the easiest way is to connect your body to your source. Congratulations. Then you will get this. Okay? But you need to be very careful. Yeah. It is impossible. It is impossible for P substrate at most. Because what is the current here? What is the current source? In next chapter, I will tell you the simplest current source is another NMOS. Okay? The body of the NMOS is connected to the substrate and also to the ground. You are NMOS, I am also NMOS. Our bodies are all substrates, so our bodies need to be connected together. So there's no way for you to connect your body to your source. No, 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 no. Your body, my body, all connected to substrate. Wow. So it is impossible for NMOS. But on the contrary, how about PMOS on P substrate? Because it is isolated by N-well, so it is possible. Okay? How to make it possible for PMOS on P substrate? It means the first PMOS here, the second PMOS there. Again, for this one, and this is for current. It is flipped upside down from N to P. Okay? This is for I, and this is for a source follower. Then you need to have different N-well. Then, bingo, you can make the PMOS without body effect. Okay? That's it. Yeah, anyway. If you would like to make both, I mean, for PMOS, for NMOS, both can reduce, can cancel the body effect. You need to have the so-called twin well process. Twin well, both N well and P well. So you put the NMOS into P well. Congratulations. It can be isolated. Okay, inside your own well, you can connect your body to your source because the P well will be isolated from the P substrate. But how? Usually by deep N well. Okay, oh, it is really complicated. But anyway, okay, that is the. All right. This is the substrate, right? If you will put your NMOS inside P well, but you have P substrate, it doesn't make any sense. P well, P substrate will be connected by each other to each other, right? So you need the help of the other one. We call it deep and well. Okay, that's it. Again, nothing is free. You need to pay for extra layers. Deep and well is not free. You need to pay for it. Okay, that's it. And the P well is also not free. You need to pay for the extra mask. Yeah. For deep and well, for P well, it's up to your boss. On campus, it's okay. Yeah, because never mind we have deep and well, P well or not, we get the same price. Especially for education chip, you pay nothing. We pay nothing. Okay, but to the industry, no, one layer means one extra mask. Yeah, especially for advanced processes, 7 nanometer, 5 nanometer. Millions of US dollars per mask, okay? That is really, really expensive. Don't touch. Yeah, second order effect, channel length modulation, I told you already. Yeah, after pinch off here, if you increase it, the length will be shortened, right? So you have such kind of effect. The effective length look like this. Delta L. Okay? You have delta L, right? So, yeah, you can see the effective L prime look like this. So overall, that is lambda for the channel length modulation. Okay, so for lambda, you can see it is proportional to this. Okay, that is a very simple equation. Yeah, so it means what? Lambda. Okay, this one. Oh, sorry. To make it clear. Yeah, it is piece of cake. Derive it by yourself. Yeah. So you replace L prime with L, the original effective length, and delta L, okay, according to channel length modulation. So after some kind of derivation, you have such kind of analogy. Lambda is proportional, is reversely proportional to L. It means what? The longer channel, the less channel length modulation effect. Okay, that's it. And then, if you are curious how the length has the impact on ID, usually maybe for students, you will guess, according to the original one, right? If you don't understand channel length modulation, if you only look at this, you will see, hey, the length is reversely proportional to the ID, right? So the impact of length on saturation current is only -1 minus first order. Okay? But in practice, if you take this into consideration, because that is the more accurate equation, not only this, but also 1 plus lambda VDS. So, and lambda itself is proportional, reversely proportional to L. So, if you differentiate ID to L, not only this, but also that. Okay, here we have one order, and there you have another order, convergulations. This is the impact of the length on your output current 2 times. Okay? I can answer 2 times. Yeah. Second order instead of the first order. It means what? If you increase the length by 4, then the current will be reduced. I mean the saturation current. Sorry. If you increase the length by 2, then the impact on your saturation current will become this. Okay? The square of 2. It means what? The length gets more impact on the output current. Anyway, I told you already, the slope ID over VDS actually is 1 over RO. Okay? I over V. RO is V over I. Right? So what does it mean? The most important impact for you is the real output resistance actually. Okay, that is the more important idea for you. If you would like to increase the output resistance, to increase the length of the channel will be the easiest way for you, more powerful than you can imagine. Okay? In brief, output resistance is proportional to the square of the length instead of to only first order of the length. Okay, the impact of length on output resistance is much higher than you can imagine. And then we go for weak inversion. That is so-called subthreshold conduction. I told you already. It looks like that. But I explained already, right? With such kind of exponential something, you will get much higher gain. But the overall current is really, really small because your gate voltage is very close to VTH, okay, around VTH. So it is not so conductive. It is almost behave just like semiconductor. The conductivity is minus 12th order than conductor, right? Around this order, wow, it conducts very little current. So you can get very high gain in this area, but the operation speed is much, much slower than in saturation. I mean in strong inversion. So that is the main difference. Strong inversion, that is what you learn for saturation. And weak inversion, you can get much higher gain, but with much slower speed. That's it. Okay? Now we can talk something about short channel. Yeah, if the channel becomes very short and you apply the same voltage, what does it mean? And again, if the channel can become shorter and shorter, what does it mean? The process will become better and better. So the gate oxide will also be reduced. Okay? So you have two impacts. First of all, carrier velocity saturation. Because with shorter length, but you apply the same VDS, the electrical field will become very high, right? So the electrons can be speed up, but after that, they need to collide with the lattice. With such kind of very frequently collision with the lattice, the speed will be saturated. Okay, that's it. That is the so-called early saturation. For long channel, it will go until VGS minus VT, right? That's for long channel. If the channel becomes too short, the electrons will move too fast and then always collided with the lattice. They cannot move even further. I mean, they cannot increase too much in speed after frequently collide with the lattice. So the speed for electrons propagation will be saturated much earlier than this. So what does it mean? The saturation current will be reduced by 1 order. Wow, that is really bad. Okay, you cannot run so long. No. Yeah, how much you can run is always saturated already. It is fixed. So the current, it will be reduced by 1 order according to early saturation. Okay. Yeah, carrier velocity saturation I mentioned already. So saturation current right now is only proportional to the first order instead of the second order. Okay. Yeah. And also, it is even worse. I told you for short channel we have not only early saturation, that is the first impact. The second impact is mobility degradation. Anyway, never mind body effect, early saturation, mobility degradation. That is all the so-called second order effect. Okay? Those are very important for analog IC designers, but they are totally not important for digital ones. They simply forget about this. All right? Now, what will go wrong if the channel becomes too short, the gate oxide becomes too thin? You can see the gate here and the silicon dioxide becomes really thin. What does it mean? For electrons, from source, again for MOS, from source to drain, right? Yeah, they would like to go there, but you put much positive voltage to the gate, and the silicon dioxide is so thin, right? So during running from source to the drain, you see, wow, that is also positive. Not only drain is positive, also gate is positive. So some of the majority carriers, I mean free electrons, especially very close to the surface of your gate oxide, they will be attracted by the gate because the thickness of the gate oxide is not good enough. Okay, so some of the electrons, especially to this, this is the gate oxide, right? Silicon dioxide. If the electrons here are very close to the bottom surface, some of them will be attracted by the positive gate voltage, right? What is the consequence? Again, not 100% of the carrier will go from source to drain. Okay? Yeah, so it means the saturation current will be reduced a little bit. That is not so harmful. The most harmful is if they get enough speed to go in that way, then the free electron will penetrate into your silicon dioxide. And then they will be embedded there, right? After you turn off the channel, you turn off the gate, okay, the MOSFET, there are still some electrons embedded in the gate oxide. What does it mean? Because they are negative, right? Right? They will, because you apply positive here, but they are negative, the electron negative, they will cancel some of the impact of your positive gate voltage. Again, we put all the blame on VTH. Okay? So it means what? The threshold voltage will be increased. That's it. Okay. Anyhow, the overall mobility will be decreased. All right? And then we can go further. For short channel, we have a lot of second order effect. Again, from the very beginning, we didn't mention about depression region. But actually, I told you already, depression region, the width of depression region depends on your doping concentration. Right? The lightly doped, the wider concentration. What does it mean? You are M plus, I am P minus. It means I get more depression region than you. But if the channel length is long enough, nobody will pay attention to the depression region for your body, for your channel. Okay? But if your channel length is so small, then you will have huge impact on the real length. Again, from the beginning of the chapter, I told you, L effect means L neutron, right? Minus 2 delta L. Delta L is according to side diffusion here and there, right? That is side diffusion. But not only side diffusion. Right now, we have also depression region. Okay, so you need to cancel not only side diffusion, but also some kind of depression. Oh, okay, anyway, small d, that is large d. Okay, and it means the effective length will be much smaller than you imagine. It means what? The resistance will be much smaller than you imagine. You will get more current. Again, we put the blame on threshold voltage. You get more current. It means what? Effectively, threshold voltage is reduced, right? Okay, so this is the so-called short channel effect. The threshold voltage will be reduced very much for very short channel. Okay? And for an analog IC designer, especially for critical MOSFET, don't design your critical MOSFET here. Why? Because after fabrication, it will become larger or smaller. And according to the slope, wow, the threshold voltage has such kind of huge variation. And according to saturation current, if you have huge variation here, it will be amplified by 2 order, right? It doesn't make any sense, right? Again, for critical device, for critical MOSFET, please design their length at this region. Here or there. Yeah. Longer, after fabrication, it becomes a little bit longer, a little bit shorter. No impact on this, right? And this is real dangerous for analog IC designers. Don't touch. Okay? But how about digital one? Who cares? For digital IC designers, they love this very much. Why? Because never mind it is longer or shorter, the VT edge in this region is much smaller than there, right? So you can speed up the operation for such kind of non-critical circuit. Bingo. Even for analog IC designer, again, critical device here, non-critical device to speed them up there. Okay, that's it. We focus on mismatch very much. I mean, analog IC designer care very much about the mismatch. So what you design, and after fabrication, the more mismatch usually means the poorer performance. Okay? So we hope during design, the result should be about the same as after fabrication. So please focus on here, this region for critical devices. But if the MOSFET are not so critical, then here, especially for your digital circuit on chip. Okay? On chip, we have analog part, we have digital part. Digital part can be here. Analog part, especially critical analog device. Please don't design there. But you can see TSMC and UMC would like to help you. So they improve their process. How can they improve? Okay, they would like to reduce this region. And how? They extend this region and down. Okay? You get something like this. To make the curve up a little bit, then go down. And it means, yeah, the steep region is much more reduced. Okay? But I still, how can I say? I still recommend you for critical devices, you still don't touch this region. Okay? Here is better for you. Yeah. The problem is not only for length, but also for width. If the width is too narrow, in the past, we have the so-called burst peak, 鸟嘴. Okay? What I'm talking about, for example, 0.35 and older. Where is the length from source to drain? Where is the width in this direction? Right? I'm talking about this direction. If I have a slide for you along the width instead of the length, okay? In the past, we have thick oxide to isolate, and this is your gate. Yeah, the width in this way. We have very thin oxide here for gate, okay? Gate oxide. And this is thick oxide for isolation. The thickness usually 100 times more for field oxide, thick oxide, than thin oxide. Okay? So how about the poly gate? Extend to right and to the left. The poly gate looks like this. From the top to the bottom, then go back to the top. During fabrication, don't expect, yeah, it looks like perfect. For your gate oxide, this is the width. No, forget about it. You don't have such kind of very sharp edges, right? The sharp edges will become smoothed here and there. So, allow me to show you. This is the width, and the sharp edges will be smoothed. What does it mean? The gate oxide will become much more to both ends of the width. Okay? The thickness the effective thickness for gate oxide is increased to the both sides. If the width is very small, then the impact will be very much. Okay? So the average thick oxide, the thickness will be increased. So the threshold voltage will also be increased, as I mentioned moments ago. So it's really upset. Okay? For narrow channel, we have short channel effect. We have also narrow channel effect for old process. You say, hey, right now you don't have such kind of process. From CIC, we have 0.18 all the way down. 0.25 will be out of date, maybe in this year, right? So for 0.18, even 0.25, we don't have such kind of burst peak. So we don't have the so-called narrow channel effect. Is it true? No. For isolation in the past, we have field oxide that is very thick. Right now, we use shallow trench isolation, okay, to get rid of the big problem here. But blah, 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 after measurement, you will see this one goes down. From old era with thick oxide for isolation, right now with shallow trench, the result are totally reversed. You get something like this. Again, never mind you have new process or old process. For critical device, please design in this region instead of that. So never mind for width or length, I need to warn you. Feature size, what do I mean? 0.18, it means the length of the width is 0.18. 90 nanometer, the length of the width 19. All those are in this region or in that region. Very dangerous for your devices, critical devices. So please don't design your critical MOSFET with the smallest length or width, because you will get a lot of variation on your threshold voltage. We put all the blames on threshold voltage. Okay? Allow me to show you one slide from Avago Technology. It is a very famous semiconductor company. Yeah, you can Google online. Yeah, this is some kind of slide from them. They spend a lot of money to have some kind of test key from TSMC, 90 nanometer, right? Not so bad process, right? How about the threshold voltage? Oh gosh, that is a result. We call it a saddle figure. Ma'an, because you look like the shape of saddle, right? On the horseback. You can see this is the width, that is the length. For 90 nanometer, it means what? In theory, the smallest width and length should be 90 nanometer, right? Okay, let's focus on width. Wow! You can see it is flat. Good for your critical devices. And it is really bad. I told you, for new process with STI, it goes down. Instead of goes up for very narrow channels, very small widths. It goes down. Again, don't design your critical devices with such kind of small widths. But how small? Wow! The turning point here goes down. Wow! Almost. Hey, you say, hey, the same. No. 0.95. It means what? See? 10 times larger than the feature size. Okay? Wow. And how about the length? Again, don't be fooled. Okay? The channel length the short channel effect goes up and then down. Okay? Because this is a new process, we have this. But anyway, goes up and down. I don't care, because you can see here the threshold voltage is only less than 0.2. But there, wow! More than 0.35. It doesn't make any sense. right? So if you would like to stay in the region, more stable region, how about the length? Wow, see, 1.58. Gosh, compared to 90 nanometer, much larger than the so-called feature size. So what lesson you can learn from this slide? Keep this in mind. Again, for critical devices, feature size is really bad for you. Never mind for your width or your length. Don't touch. Okay? It is really harmful. If you wouldn't like to get the measurement result after fabrication, wow, what? So bad. Okay? Critical devices had better be here. Right? Anyway. Threshold voltage variation. Yeah, I explained all those already. Put all the blame on this. Okay? Anyway. Hard carrier effect, hard electrons, drain-induced barrier loading. Oh, all right, too much. Okay? I explained many kind of second-order effect. I guess some of you, or even many of you, were confused. All right? But anyway, my only purpose is to tell you, is to warn you, what you think, what you learn from microelectronics, I cannot say it's totally incorrect. No, it's not accurate enough for analog IC designers. Okay? You need to pay a lot of attention to the so-called side effect. Okay? Good enough. But for the absolute value, you don't need to memorize all of this, right? Not important at all. Not important at all. Okay? For this, for that, again, the most important recommendation is here. For the stable period, yeah, the width, the length for critical devices needs to be much larger than your feature size, especially for such kind of good processes. Okay? Again, if you ask me, what is my rough recommendation, absolute value for the length and width? Okay, 1 micron will be a very good starting point for your critical devices. Okay, but it still depends how critical your device are. All right, that is the beginning, good starting point for you. But if you are curious, again, you can run Monte Carlo simulation to check how small you can design for your critical devices. Okay? Monte Carlo simulation can help you solve this problem. Okay? Anyway, that's for long channel. You can see the dependence I told you already. It is quadratic. Okay? Second order. But for short channel, according to early saturation, the dependence becomes only linear. Yeah, only the first order of your VGS minus VT, blah, blah, blah. Okay. So with early saturation, almost 40% less current than you can imagine. That's it. Okay. You have linear dependence here. Anyway, early saturation. Yeah. Again, quadratic for long channel, for short channel, it becomes linear. The only good issue for such kind of linear dependence is the current and the voltage. They are linearly dependent on each other here, right? So less distortion. That is what I mean for large signal. For large signal operation instead of small signal. For small signal, if your signal, the amplitude of your signal is really small, everything is linear. Okay, even here. Hey, you can say, hey, that is parabolic. But if you operate at very small region, it is linear. You submit, it's still linear, right? So for small signal operation, everything is linear, but for large signal operation, especially to the final stage, it cannot be very small, right? Yeah, for final stage or final stages, this one will provide better performance, I mean according to distortion. Okay, but you need to pay the price. The magnitude, the gain will be reduced very much. Okay, nothing is free, you need to pay for it. Yeah, a few moments. Sorry, I need to finish this chapter today, because for next week, we need to talk about the design for current source. And after that, 2 weeks later, I will attend a conference in Japan. I won't show up. So 2 weeks later, we will have the first homework according to current source. So I hope before you go to the computer lab for homework, you already know something about the circuit you need to design. Okay? So today, a few minutes, I finished chapter 3 for you. Then for next week, we can go for chapter 4. Yeah. Anyway, I told you already, we have body effect. How can you reduce the body effect? We need the body contact, right? My recommendation is for body contact, it needs to as close as to the main body of your channel or the MOSFET, as close to as possible. Why? Because for 0.18 process, I think many of you focus on this, okay? Unless you design very high-end chips. Otherwise, 0.18 is a very good platform for you to get enough experience for your future. 0.18 good enough. Anyway, I told you already, all those process, all the technologies are created for digital IC designers, not for us. So there is a very ridiculous example for body contact. According to 0.18 process, to my memory, the body contact can be as far away as 25 micron or 20, at least, to my memory, 25, at least 20 microns, far away to the main body of your MOSFET. Why? Because for digital chip, after APR, they place all the logic gate and do routing, right? After they can punch such kind of body contacts. So it's easier for them to realize everything. Because after APR, very few space left for such kind of body contact. So they can tolerate 25 micron in distance. But for us, hey, if it is not here, it is there. You apply your body voltage here, right? But how to conduct your body voltage all the way to your channel? Hey, it needs to go through P- substrate. P- or N- means very high resistance. Okay? So it means the voltage for your body contact there and the real voltage for your channel should be different. And usually it will impact your threshold voltage. Usually it will increase your threshold voltage. It is really harmful for analog IC design. Okay, so my recommendation for you, even you say, hey, I put the body contact there according to DRC, nothing wrong. DRC. I told you already, I warned you already. Even though you fit all the requirements for DRC, it's still far less than enough for analog IC designer. Okay, so even for this kind of body contact, my recommendation is as close to your channel as possible and as many as possible. One means not good enough. Why? Because sometimes you have very wide transistor to conduct current. Okay? And if you only punch the body contact here, from here to there, your channel, too far away. Okay? The threshold voltage here usually will be increased a little bit. So hopefully you can punch many of the body contact around your critical MOSFET. Okay? Get it? Yeah. So usually that is a very good habit for you. After you do the main layout for your MOS, MOS here, MOS there, MOS here, MOS, and how about the empty space? If possible, you have quite many contacts for PMOS and quite many contacts for your NMOS. It will help you to enhance the performance of your overall circuit. Okay? That is my recommendation. All right? And then we have a lot of parasitic capacitance. I told you already. Just have a look. Wow, very serious. Okay, and then try your very best to reduce them. That's it. But how can you reduce them? Very careful layout. And also, we have MOS capacitor. How to make such kind of MOS capacitor? Oh, okay. Right? You can connect both your drain and source to become one terminal, for example, A. And the gate, the other terminal. That's it. Source and drain are shorted. Then the behavior look like this. What we need? Why we need such kind of very strange capacitor? Because for communication, usually we need to tune the frequency. Okay? And how to tune the frequency? Usually we have LC oscillator. So the frequency, right? Can you tune L? No. So the easiest way is to tune C. And this will help you to make it. That's it. Okay? To replace such kind of very bulky, 很大一支的 varactor 变容器. Okay? And again, in my previous class, I warn my students very much about the layout. For example, this is your source or your drain. For NMOS, inside it is N+. Outside, it is surrounded by P minus P substrate. With P and N, you have PN junction. PN junction means what? A lot of capacitance. Okay? So for such kind of area, for 3-side wall and the bottom plate, you have parasitic capacitance. But for the side wall with the channel, your N+, the channel is also N+, so no PN junction at this side. Got it? Got it? If you would like to reduce the so-called a lot of parasitic, okay, you don't need to memorize all those. Forget about it. But during layout, you need to reduce the 3-side walls and the bottom wall. That's it. The bottom plate. But how can you make it? This is, okay, 3-side wall here, 3-side wall there, and the bottom, right? But the side wall adjacent to your polygate, to your channel. Okay, nothing will go wrong. Very little parasitics. You need to reduce those 3-side wall and the bottom plate. How can you make it? Stacked layout. You can overlap this with that. See? Okay. Got it? From the beginning, you have only one. If you cut one into two, then overlap it. See? For the central region, because it is overlapped, so the bottom plate is shared by both, right? So it is divided by 2. And then for the side wall, only here and there you have parasitic capacitance, but this and that, no. So what I'm talking about is for a wide transistor, you just cut it. That is the width. You cut it into half width and overlap with each other. That is the so-called stacked layout. It can help you to reduce the parasitic capacitance very much. Okay? That is the easiest way and the most recommended layout pattern for you for very wide transistor to reduce the parasitic capacitance to speed up the operation. Okay? Finally, is it finally? Oh, not yet. Okay, yeah, some more minutes, sorry for that. Junction capacitance. In chapter 2, I warned you already. For diode, for reverse diode, I show you this, right? Right? That is Q over V. The more voltage, the less Q can be fit in. Okay? Anyway, the capacitance is reduced. So that is Q over V, and this is C over V. Here, for reverse, the same. Yeah. The more reverse bias, the smaller capacitance, because the slope becomes smaller and smaller. Okay? And I warned you already, that is for reverse bias. And how about forward bias? It looks like this. The capacitance will be increased substantially, just like this. So what I mentioned to the end of chapter 2 actually is exactly the same as this. But that in chapter 2, Q versus V, and here, capacitance versus V, and include both forward bias and reverse bias. And this is the reason why usually for a channel, we don't operate here, because it will induce a lot of parasitic capacitance. Okay? We usually have reverse bias for your channel and body. Yeah, you must be very careful. And the other one you need to be very careful is this, parasitic SCR. What is SCR? Don't ask me. That is for power electronics. Okay? But the structure looks like this. Yeah, that is for you. You have PMOS, you have NMOS, you have NMOS, you have PMOS and NWell, and then you have such kind of very strange architecture. That is the so-called SCR. Okay, you don't need to know what is SCR, but you need to know the IV curve of such kind of structure. It looks like this. And for our usually operation, VDD is here. Okay? All right? So you turn it on, you turn it off. If you turn it off, it will be cut off in this way. But according to spikes, I told you, on your VCC, it doesn't look like this. Sometimes there are spikes, spikes, spikes. For such kind of upward spikes, if it is too much over this limit, okay, go up, then go down. Oh, two possibilities. One goes back to 0, cut off. The other one, oh, sorry, it will stay there. Okay? Wow. Well, what? You already turned it off, but actually, unluckily enough, after the spiking, the spikes, it goes down here, then the circuit won't be turned off. Yeah, you can see a steady current is flow from here to there. It wastes you a lot of power for that. Sometimes the chip will be burned because everybody conduct large current, okay, from VDD to ground for everybody. Okay, so it is called latch up. Okay, what you can do? Two issues. To make sure nothing will go wrong for your circuit, please, for your VDD, don't get such kind of simulation from this time, right? For your transient simulation, from 0 to infinity. Oh, your VDD is a DC 1.58 for your circuit. You don't have chance to check such kind of SCR parasitics. What you can do is to real turn on your circuit. What do I mean? For your simulation, VDD is not a DC. It looks like this. Okay? Usually around 10 nanoseconds, as you like, longer or shorter as you like. From 0 volt to the real VDD, 1 point value. So you need to the help PWL, piecewise linear model. to pull up your VDD from 0 to the regular value. If something will go wrong, then during the process, it will be latched. Okay, a lot of current will be leaked. Blah, blah, blah. Then hey, something wrong. So that is the first check. But after that, what you can help yourself? Very easy. To cut off this and that, how can you do? Reduce the resistance. Okay? The more resistance means the more voltage to be likely turn on this and that. Oh, that is really bad. Okay? But how can you reduce the angle, the P substrate resistance? More body contact. As more as possible. Okay? Okay? If for the space inside the angle or outside or in the P substrate, for the space area, empty area, you have a lot of body contacts. They can be reduced by body contact. So that's the second reason for you why I recommend you a lot of, as many as possible body contacts for your empty space. So usually for our VCC and the ground, VCC always have some kind of body contact for your PMOS. Let's say your case. And for your ground also a lot of body contact for your MOS. But in between, because your PMOS here, your MOS there, you have empty space. Oh, body contact connected to the ground, and body contact in angle connected to your VDD. That is a good habit for you. Okay, that's it. To be a very good IC designer, you need not only to be very good at design, but also layout. Okay, that is what you can help yourself. Yeah, that is some kind of small signal model, blah, blah, blah. Okay. Anyway, I would like to tell you that the overall GM, that is what you learned from microelectronics, right? And this is what you learned today for analog IC designer. Pay attention to your body effect. Usually you cannot get rid of the body effect. Okay, no way. Then you need to be careful. GMB equivalent to GM by this constant, EDA. How much is EDA? Usually, see, 10% to 30%. If you are lucky, it means what? The overall current, the transconductance will be increased by 10 to 30%. But unluckily enough, usually they are contradicted to each other, right? So the overall gain, the overall current will be reduced by 10 to 30%. If you don't have a good, you don't take a good care of your body effect, you will get such kind of loss. Okay? Yeah, complete CMOS model. I would like to tell you, it is more complicated than you can imagine. But who can help? Our EDA tools, our models. Actually, the real model is much more complicated than this. At least, again, one order more complicated than this. Okay? Yeah, but you can help yourself. You know, that's too complicated. How can I help myself? Again, if you have a wide transistor, then you cut it into 2 or into 4 or into 3 as you like. Then connect them parallelly, overlap with each other. Not only the parasitic capacitance will be reduced, but also the parasitic gate resistance will also be reduced. See? That is the length for your polygate, right? You cut it by 2. So for each one, the resistance is reduced by 50%. But you connect them in parallel, so another reduction by 2. So overall, the gate resistance will be reduced by 4. Okay, got it? So the more fingers, the better you can reduce the gate resistance, and also the parasitic capacitance for your channel. Okay? Anyway, what is my recommendation? For a single MOS, after you cut into many fingers, the final stack layout as close to square as possible. 啊，你给它砍做好几节，然后把它并在一起，最后看起来很像一个正方形。That's it. That is my recommendation. Okay? Spice model. If you have a look at, please go back. If you have some kind of IC design server, you can have a look at the technology file for your spice model, NMOS or PMOS. I promise you, again, yeah, at least one order more than this. What do I mean? For your NMOS or PMOS model, they are right now, I think, more than 100 parameters. Okay, I am supposed to be a very experienced IC designer, but even though I don't touch the real design, but I get very good logic thinking, understanding. How many parameters I know? I promise you, less than 10. Okay? So the detail is not important. The important is you need to know there are a lot of parasitics. Try your very best to reduce them. Good enough. So for the layout, I don't have time. Yeah, that is what you need to do by yourself. Okay, wow. That's it. Yeah, that is for today's class. Hopefully, you get much better understanding about the operation of MOSFET. If you cannot make it, if you don't get good enough understanding about the MOSFET, then you won't be a good analog IC designer in the future. Okay, so this is the first help I can do from the very beginning. Introduce semiconductor physics, go to the simplest device, diode, and then the major device, MOSFET, for our analog IC design. After that, we can go for real circuit design. And again, from the very beginning, the simplest analog circuit is current source. Okay, so that is the topic, the focus of our next week and the homework 2 weeks later. Thank you.